Matthias Langelaar, who is Associate Professor of Structural Optimization and Mechanics at TU Delft. And the title of our first talk is Different Ways to Impose 3D Printing Overhang Restrictions in Topology Optimization. And as always, if you have questions, just drop them into the chat during the talk, and then I'll call for you to come and ask your question at the end of the first talk. Okay, Matthias, take it away.
Thank you, William, for the kind introduction, and also thanks to the organizers for inviting me to be part of this interesting workshop. And well, maybe a third word of thanks there for the two other presenters this morning, because actually, yeah, you helped a lot in introducing the topic already that I will be also talking about, namely, yeah, overhang restrictions in topology optimization. Still, I will also include some introduction of that for the people who just joined or maybe in the YouTube channel clicked accidentally at this part of the whole event. And yeah, maybe a last word of thanks then to all my colleagues who have participated also to the work that I will be showing. So that's Emil, Rashid, Can, and Fred, all from the group in Delft. So with that, yes, yeah, let me start by saying that I'm really fascinated by additive manufacturing and the way the technology is developing. It can inspire people to create very beautiful looking structures that also are functional, such as this part of a car I probably never will own myself, but it's an expensive sports car, but it's an optimized brake caliper created by metal additive manufacturing. So looking like this and set in a nice photographic session, it looks very nice. But there's also, I would say, a more ugly backside of additive manufacturing, and that is if we look at the actual manufacturing process itself. So if you look at how this part is actually created, it doesn't look so nice and shiny as we saw in the previous picture. It looks more like this. And in particular, what is not to like here is all these structures here, the so-called support structures, these extra structures that you need to print as well in order to make the fabrication of the entire part possible. Well, that wastes some amount of material and some amount of printing time, but even worse, it wastes a lot of, it creates a lot of post-processing time to get rid of these structures because it's metal fused to metal, and it takes quite some force and effort to get to the final part, like you saw in the previous slide. So this is a point of attention, I would say, in metal additive manufacturing, and most of the things I will show are inspired by this problem. Okay, so this is an outline of what I want to discuss for today. First, I will give a brief introduction to topology optimization. This may overlap with some of the things the previous speakers have mentioned, but maybe also I will put some accents on some parts not mentioned yet. Then, yeah, very quickly, discussion of additive manufacturing. I think this audience, for this audience, it's not necessary to go into much depth there. Then, yeah, as the title of my talk already showed, the focus is on overhang constraints. So I will define that and then look at 3 different ways on how you can address that. In fact, this is not complete. There will be other ways. I believe, even judging from the title, that the next talk will also be about overhang constraints and yet a different way of handling them. So I think this is nicely complementary. And just also from an engineering and mathematical point of view, it's interesting to see how many ways you can define such a restriction. So we'll talk about first a geometrical approach that is basically devised for regular meshes, then an extension of that to arbitrary meshes, and finally also a physics-based overhang approach, you could say, and at the end some conclusions. So let me start with a quick introduction on topology optimization. This is a computational design technique that allows engineers to generate an optimized material distribution. So you can think of having a certain amount of material to spend, and it should be placed somewhere in this box in order to create a certain functionality. And the intended functionality here is that we have these blue arrows here at the back. They are the inputs where we apply forces. And what we like to generate is a mechanism that creates a gripping force at this green arrows at the output. Yeah, so it's like a kind of twisted gripper as the motions are not in the same plane. And yeah, I guess as a designer, it could be quite a challenge to come up with the right shape for this. But with topology optimization, we can, yeah, let the computer do this material distribution work for us. And basically every frame in this movie is one step in this optimization process where such a material distribution is refined until it has the right and the required functionality. So here you see a simulation of this gripper from a side view and a top view, where you can indeed see that it is moving as intended. So that in a nutshell is a topology optimization, at least of what it can do. Now, from a more mathematical point of view, or at least from the process point of view, how does this work? There are different approaches to topology optimization. We saw already this morning as well. I will be talking about the so-called density-based topology optimization, where we describe the component by means of a certain density field, a material distribution by normalized densities. And these are here depicted in black and white. So the black part is where there is material and white is where there's no material. This density field is input for a finite element analysis, typically, where we can evaluate the stiffness, the displacements in case of the gripper, or the stresses, or any other kinds of quantities that we're interested in. And these end up in our optimization problem as either objective or constrained contributions. I've summarized those here in this term Fi as arbitrary responses for the optimization problem. That information then goes to an optimization algorithm. Typically in the field of topology optimization, method of moving asymptotes is very popular. It's also used in the examples in this work, and that produces a new material layout for the next iteration. Now, one ingredient is missing here, and that is that we use a gradient-based optimization approach. So we also need gradient information, so-called design sensitivities, which is essentially the derivatives of the responses that we are interested in with respect to the design variables that we are controlling. So calculating these is an important part, because otherwise we cannot do an efficient gradient-based optimization. Now, if we analyze where the cost is in this computational process, it's one component of it is that it's iterative. So this loop is typically performed order of magnitude 100 times or hundreds of times, which already adds up because there's expensive simulations in the loop. The most expensive parts in the loop are typically the finite element analysis, so the response calculations, and also, depending on the problem, the sensitivity analysis can be also quite expensive. And the other parts are typically of lesser impact. And yeah, this sensitivity I already mentioned in the previous slide is an essential ingredient. Without having this gradient information, we cannot do any efficient optimization, because the number of optimization variables involved in topology optimization is typically thousands, 10,000s in two-dimensional problems, and easily millions in three-dimensional problems. So that's really large-scale optimization for which you need gradient-based techniques. The cost of this design sensitivities depend on the type of problem you are considering. So for steady state problems, it's a lot more friendly than, for instance, for transient problems and so on. For today, I will only look at steady state linear elastic problems. And finally, a consequence of the important role of the design sensitivities is that all the models in this chain that I have drawn here must be differentiable. Otherwise, they do not have a derivative, and we also cannot calculate them. So differentiability of models is something that will come back also in some of the approaches that I will discuss. Okay, then a final introductory slide about topology optimization. Also in this talk, I will limit myself to a particular type of design problem that's very often studied in topology optimization, also an important problem in practice, and that is so-called compliance minimization, where we have a certain mechanical problem where we again want to devise a optimal structure with minimum compliance. So that means actually it should deform the least under the action of a load, or in other words, the stiffness should be maximized. That's another way you can see it. And that is done under a volume constraint. So we are restricted the amount of material that can be used. And as I mentioned, I will use linear elastic analysis, mechanical analysis in all of the examples. Okay, so that was a quick overview of topology optimization and some points of attention. So what is the link between additive manufacturing and topology optimization? Well, first of all, it was of course great when I had generated this gripper that there was actually a technology that allowed to make it, because making this with traditional milling or turning or other operations would be very difficult given this complex geometry. But with additive manufacturing, with printing techniques, such complex shapes can actually be realized. So that's very nice. We can finally realize these optimized and complex devices. And on the other hand, technology like additive manufacturing, where you have such an enormous design freedom, how to shape your parts, almost anything can be fabricated. That design freedom, to benefit from that, you need for complex problems some kind of computational design tool to fully benefit from that. And topology optimization is a very nice approach for that, I would say. So these two technologies, essentially reinforce each other in this way, and that's why it's a very interesting combination. But it's not without problems. And then we come to the overhang restriction. So already also this was introduced this morning, so I will be brief on this. But in many additive manufacturing technologies, there are limits to the angle that an overhanging surface can make with respect to the substrate. Typically angles in the order of 45 degrees are still printable without adding supports, like I showed in the brake caliper example at the beginning. But if it is a more shallow angle, then in order to print this properly, you have to add support material in order to not get defects, such as you can see here in this test example of a horizontal overhang, where the material, while being heated by the laser spot, essentially has sagged through the powder in the powder bed and creates these kind of not so nice results. So to prevent these problems, what's typically done in practice is that support material is added, like we've already seen at the start, and addition is one thing, but after that you also have to remove all this, and all of that is adding cost and time and effort that we would like to avoid. So the challenge is to come up with designs that still have the right functionality that we are looking for, but that do not have this problem of violating the overhang restriction such that so many supports are needed. Now, this problem has been recognized in the field quite early on already, and there have been quite a lot of efforts on how to deal with it. Very nice also that especially first speaker, I think, showed this type of approach as an example, that you can basically place a constraint on the angle of the boundary. Here's my pointer, of the boundary of the shape that is generated. And then you get a geometry that indeed everywhere meets, for instance, a 45-degree overhang angle, except it's still not printable because these points that are floating here in the air, if you think of the powder bed process, there would not be a proper solid place to start this part of the structure. So this is in the end, not a complete way to restrict your optimization process to manufacturable designs. Meanwhile, there have been some additions and refinements on this approach where you still make use of the density gradient. I suspect maybe the next speaker will tell me or tell us all more about that. What we have followed in our efforts is mainly an approach where we try to apply a simplified printing process actually within the simulation, so that we can make sure that whatever comes out of the topology optimization process is printable, and that the printed shape performs as it should. Here you see some pictures. I will come back to some of them in the later slides. And a third way, which I will also show as the last option that I will discuss today, is to use a certain physical principle. So this was already nicely introduced by Charles, of using the weight, for example, of the roller or the self-weight of the part in order to give the optimizer an incentive not to make any kind of overhanging structures. Well, also this I will show an example of. But first I will focus on these more geometry-based approaches. And I will start with an approach where we also make use of the structured nature of meshes that are typically used in many topology optimization procedures. And to explain that, this is the setting. We are considering a part that is going to be fabricated by additive manufacturing. So we will have in the end all kinds of layers deposited on top of each other. And we are also in a setting of a density-based topology optimization. So if we would make a mesh of this domain, it would be a structured mesh aligned with these layers. And each element in this mesh would be associated with a density variable. Now, the idea is to formulate essentially a process model that allows us to generate a printed part given a certain input field. And the input field is what you see depicted here, as I call it the blueprint density field. So this is something that the designer provides or the optimizer provides. And suppose that the bottom layer here is already printed. So now we have a new blueprint density that is placed here in this position. And now we introduce a geometric rule that we say in order to print something on top of a previous layer, its density should not be higher than the maximum density in the previous layer, because then otherwise it would not be properly supported. So we calculate the maximum supporting density of this set of three elements, so taking the maximum of these three densities, quite simply. And then we compare that to this blueprint density, and we take the minimum of these, because the maximum support capacity is this. So if the blueprint density is higher, it should be basically overwritten by a new density, which is the minimum of the blueprint density and this support density, so that we never print anything that is more dense than the maximum of the region that is supporting it. And this is actually two statements, maximum of these three densities, and then taking the minimum of that result and the given blueprint density. And that gives us the value of the as printed material, you could say. So this is a very basic and simplified process model. There's no mechanics or thermal simulations involved, but it allows us to detect or actually eliminate regions that are overhanging. Now, there's one caveat here I should mention. In introduction, I told that the gradients are very important in this optimization process. So I should make sure that these max and min operators are actually differentiable. Otherwise, we do not have a proper gradient. So for that, we use these smooth approximations for the max and min operator. Okay, to show how this works, even though it looks quite simple, two simple rules, I should also mention we apply it layer by layer in the same fashion as the whole entire printing process is also a layer by layer process. And this small animation will show, as we proceed layer by layer, that certain regions of this layout, this was actually a topology optimized beam using standard topology optimization. Let me go back. This is what you get if you do the normal topology optimization without any fabrication constraint for this problem. If you apply this printing filter, you could say, it filters out the regions that cannot be printed, like the large overhang that was present over here is now gone. And we see nice 45-degree angles, which is the limit for self-supporting printing surface. That's caused because of the regular mesh and the fabrication rule that we just introduced. So now the idea is, now that we have this geometric, you could say process simulation, very much simplified process simulation, but it identifies which parts is the printable part of a certain geometry. What we're going to do is, this is our standard topology optimization loop as I introduced it. I'm just going to place an operation in between here, that the suggestion that is obtained from the optimizer as a next design, I call that now the blueprint design. And that goes through this, let's say, additive manufacturing filter, which filters out the parts that can actually be printed. So this is the simplified printing simulation. We print the part, we get this geometry here, and from this geometry, I evaluate its stiffness, its displacements, its stresses, and so on. So this is the actual printed part I consider that is to be evaluated. Now, clearly, it's not going to be so stiff in this case because we took a big chunk here out of this top beam, which is quite important mechanically. So the optimizer will make an effort to actually make sure that this top beam is printable by supporting it, as we will see in the next slide. And in that way, going through this loop and providing also the right information to the optimizer by also calculating the gradients of this printing operation, we can actually arrive at printable designs. Okay, so let me illustrate that here with an animation of the same problem, but now with this printing filter in the loop. So you see the evolution shows that initially it was rather a gray part, but because gray elements can basically build on gray elements. But as the design is converging, you see that we get all these 45-degree slopes everywhere and well-supported regions. And it is actually impossible for this process to end up with something that is not printable, because the only thing that we evaluate is actually a printable design. So it's not a constraint. It's really because it is in the optimization loop and it transforms the density field. What you end up with is always something that is fully printable. If someone wants to play around with this algorithm, there's a MATLAB code available with this link. Yeah, it's not a nice link to remember, but perhaps if you are interested, you can also always send me an email. Okay, that was in 2D, and that's how we got started, and also a good way to explain how it works. But of course, 3D printing is intended for 3D objects. So here's an example with a beam, similar case, and here actually the whole algorithm works in the same way, except that now instead of 3 elements that we consider as the support area, we have now this region of 5 elements. I've also played around with using 9 elements, but it didn't seem to make a big difference. So this is the most efficient way of doing it. And if I apply this printing filter to the result of a standard optimization with the standard topology optimization, you can see that this is the printable part that remains of this shape. So a large part here is an inner cavity has disappeared. Also a large part at the back here has disappeared because it's completely overhanging. And that would clearly not have a good mechanical performance. But if we include this printing process, let's say in the optimization loop, we get the design where, if we look at it from the back, we get these 45-degree shaped beams again, well supported by the other parts of the structure. So in fact, it forms a self-supporting structural part, and its performance is entirely comparable with this result without the manufacturing constraint. That is a peculiarity from the compliance minimization problem, that it has many similar quality optima. But in this case, yeah, it's much better to have this one than this one. Now, from there, you can extend, because demanding that a part always is self-supporting is quite restrictive. And in practice, you may actually want to use some supports if you can remove them with not too much effort, if that makes a big difference for the quality of the part itself. So that you can do by introducing a second density field. So we have a density field for the part and a density field for the support, so you can distinguish the two. And yeah, this is something I actually already had it in the presentation, but I have added a slide on this because it was discussed this morning so nicely. A big choice in this whole process is the orientation of the part. And normally then we leave that to the designer, but in fact it would be nice to optimize this as well. Well, this is something we've also worked on, and we'll briefly show a bit of that. So this as a little bonus, let's say, because I just added it before, right before the talk. In order to optimize the build orientation and account for overhang simultaneously, one approach, which we tried, I'm not convinced it's the best one, but one approach is to take your design, actually reorient it in a domain, Add also some support material by taking the union of two density fields. That gives us the blueprint fields that I just described in different printing orientations. For these, I apply this printing filter in order to get the printable domain that's indicated here in the black part. And then I take all the printable domains together of all these orientations. So the common part that is printable in all directions, I consider that as the product, as the printed part. Then I have to cut off the supports by taking the intersection with the original design field, and that leaves me with the component that would be the yellow shape here in this drawing. I know this is going maybe a bit too quick to fully appreciate the detail of it, but I just want to give the indication of how this could be done. So by simultaneously considering all orientations, a certain set of discrete orientations, we then form an objective that consists of the compliance, so the mechanical performance of this component, plus some term related to the support cost of the orientation with the lowest support. So this is again also a kind of continuous min function where we put an emphasis on the lowest contribution and the standard volume constraint. And to give you a quick idea of how this works, so what we're doing here is we have again this beam problem, and now we're going to take 72 orientations. That's my discrete orientations, and I optimize them all at once, considering all orientations and emphasizing the one that gives me the best, lowest support. And this is what came out of this process. So at this particular angle, at this particular orientation, the performance was best and the amount of support was the least. Whether it's realistic to build a part like this doesn't look very stable, so I still need to look into that. But at least in terms of the criteria set, it was the best one. And yeah, is this really good? Is this a good result? Well, to judge that, I also evaluated for all 72 orientations, standard topology optimized designs with optimized supports. That's what is here in the red box. And also topology optimized results with this overhang constraint, like I just explained in the previous part. So comparing to all of these, both the red ones and the blue ones, this is the, let's say, a performance comparison. Here on the horizontal axis, I have the orientation of the different 72 cases. And here I have the total value of the objective, which is a combination of the mechanical performance and the support, amount of support. The design that this combined approach delivered was here at 295, so that's about here. And we can see it's not the global optimum. There's actually a better design over here, but it's close. And you can also see that this orientation shows a rather multimodal behavior, so that makes it a difficult optimization problem to optimize for build orientation. Still a nice challenge though. This is a histogram of the blue design, so that's the ones optimized for overhang. And the design that was obtained by this combined approach is here at this position. So there are a few that are actually better in this distribution, but for the cost that it's 2.5 times more expensive than doing one single optimization, because the geometric filter is really inexpensive. It is still, I think, a decent result. But there's room for improvement here. And I must say, I have not found the time yet to try this in 3D, because then it becomes a different challenge that you have to sample more orientations. Okay, let me now move on to the second approach, and that is also a geometrical approach, but now using a different method in order to also apply to unstructured meshes. Because unstructured meshes, many parts that are already partly predefined, and where you want to still do a topology optimization, they cannot be meshed with a structured mesh. And we have typically these kind of tetrahedral meshes. So also here, we would like to enforce overhang constraints in some way. There's different things you can do. You can map these meshes to a structured mesh. That's something we have done. But here, what I will show is how you can also have a different overhang control for arbitrary meshes. And this is based on a different way of representing the printing process and detecting the printable area. And for that, we use front propagation. We consider a domain, for instance, like this one here, and at the base plate, we we take that as a start of a front propagation process. So you can think of a field that is propagating from here, and you generate a time field that indicates the time it takes for this field to arrive at that particular location. And what we would like is that this field can essentially identify what is the printable region, or also identify what is the overhanging region that cannot be printed. And in order to do that, in order to do such a front propagation, there's this Eikenol equation that governs it, which says that the norm of the gradient of the time field is equal to 1 divided by the velocity function at that point. For an isotropic or for a constant unit velocity, you get the sign distance function that was also mentioned this morning. But we are not going to take a constant velocity. We want to take a velocity that actually creates this type of shape and identifies the printable region. But for that, an obvious choice is to take a 45-degree angle, or whatever is your overhang angle that you can print, and have a zero velocity in other directions, so that you cannot reach the parts that are not printable, and have the same velocity in all printable directions. That would create a nice field that indicates the printable region. But for numerical reasons, this is not a very nice velocity field to work with, because you get here velocities that are zero, which from this term you can see could be problematic. So instead of doing this, we use our choice to take a rectangular or square velocity profile. So in different directions, we have different velocities. And that creates a time field that looks like this if you apply the front propagation. And that's not quite what we wanted in order to identify the overhanging region. But fortunately, there's an easy way to come to that. And that is by subtracting actually the height of the layer where you are at that moment. Then in this whole region, the front has traveled at its maximum speed in upward direction. And basically subtracting the height sets it back to zero. But in this region, the front has been delayed. It had to move around this overhanging corner. And that is why while subtracting the height here, we are left with this, you could call it a delay field, which is given by this time field minus the height y. So that's how we can identify an overhanging region. Now, a few more implementation aspects of this method. In order to do the front propagation, we use a well-known method from Setian and Vladimirsky, the so-called ordered upwind method. And that allows you to essentially quite quickly generate this field. So the computational cost is not high. For topology optimization, the domain is not given by clear boundaries, but we have this density distribution, and we should make sure that the front is propagating in the black parts, but not in the white parts. And for that, we scale the speed function with the density. So we lower the speed in the void regions by multiplying it with the density in order to slow down this propagation. And finally, this is not the result that we are looking for. We want to identify which part of the structure is printable and not have this field here, this delay field that indicates the overhanging region. But we can transform the one into the other by essentially creating a printable density field that drops off exponentially with increasing overhang value. So this t minus y, this delay field, as it increases, it would decrease the value of the final printable field. So with this plot would transform into something like this, where we have a solid material in this printable part and density that is quickly dropping off in the overhanging part. So those are the main ingredients. And with that, essentially the way this is used in topology optimization is the same as before. So this is the same scheme, the same place where an AM filter is placed, except that now the content is not this structured mesh approach, but this front propagation based approach. And also here we need sensitivity information, but this time we need sensitivity information of the front propagation process, because that defined what the printed part looks like. Unfortunately, that turns out to be something that we can also get at low cost. This artistic picture that Emile, the PhD student, made shows all the dependencies of within the time field of where the information came from in the front propagation process. And this you can build up in the forward process of creating the time field. And the sensitivity information you can get by essentially executing a very long chain rule going from the endpoint of the whole dependency chain back to the beginning and accumulating all the sensitivities. So also that can be done at low cost, in fact, even at lower cost than the forward propagation. Next to that, we have worked on coming up with an efficient parallel implementation to do this in 3D, which was not entirely straightforward for a front propagation problem, at least not to us, but it worked out. And as you can see from this example, it can handle quite large scale problems. This is a problem, a test problem where we have this hook, so predefined surfaces, the blue and the red surfaces. The hook is clamped here on the green surface, and a downward load is applied here on the red surface. The build direction for printing this part is as indicated. And here at the detail, you can see the scale of the mesh we used. I think it might have been a little bit more than really needed, but it was also for us a nice test case to see how the algorithm scaled. And here is a result of this process. So it was, I think it included something like 30 million degrees of freedom. So this was really a good test of seeing how the scalability was. I think per iteration it took in the order of a few minutes, so that was still doable. And you can see that the technique to control overhangs has worked well. So here we can see, for example, a typical shape that you get when you are dealing with an overhang restriction. This is viewed from below, so here you cannot easily recognize that, but the end result did not contain any critically overhanging surfaces. And also this, we are extending further, for instance, by also here relaxing the requirement that the structure itself must be self-supporting completely to a situation where it should also only be self-supporting in areas where we cannot access the surfaces for constraint removal, for support removal. For instance, here you see a two-dimensional example where we have a self-supporting part. Also in these, let's say in these holes, you see that the 45-degree angle is imposed. Actually, you would only like to impose the 45-degree angle in the regions that you cannot access. And I should say also here, for instance, the 45-degree angle is imposed, and also here. But those regions, you can actually place supports and reach them from outside and remove them afterwards. So that is something we are considering. And various applications, for instance, here, this is a bike part. Maybe a bit more accessible than the sports car part I showed in the beginning. Okay, that leaves me with some time to also show you something about the third approach, which is based on a physical simulation, a thermal simulation in this case. And that is based on the observation that overhangs and overheating, basically are often occurring together. So this is not directly an overhang constraint, but we try to actually prevent also the physical problem of overheating during the printing process. If you do a thermal simulation of a certain part, you see that in the overhanging regions, we see that there the high temperatures occur. This is the indication of the temperature field. And particular in regions where the heat conduction is limited, such as this funnel shape here, we have a larger, bulkier part, and that basically the heat has to go through this thinner part. That is a place where the temperature can rise to a level that it actually gives problems. And these problems can occur very visibly, like this dross formation. So that's like over melting and too much material is here is fused. But it can also be more subtle in the sense that your material properties get affected. It might not be something you can see by the naked eye. Here, for example, you can still see a discoloration in the material, but in other cases, you might actually have to do very detailed investigations to see the change in material properties, but it can occur because of the wrong temperature window that the material finds itself in. So controlling the temperature is a very relevant thing to do for additive manufacturing. And also here I come back to my standard scheme. And if we think about how we could do this, it essentially requires that we do another simulation next to the performance simulation for the mechanical objectives. We need to do a process simulation so that we can also control the maximum temperature, for example, that occurs during the process. Now, this is a quite expensive proposition because AM process simulations tend to be quite computationally involved. So in order to make it possible to do something like that within an optimization loop, we have to apply some simplifications. We start out with one of the simplest models, thermal process models we could find in literature, that uses a layer by layer approach. So it basically deposits a full layer at once instead of following really the scan path. And there are some simplifications in the physics. For instance, only conduction effects are included. All material properties are taken as constants and the phase transformations are not modeled. But this was not enough. This would still take way too long. So we have to simplify this further. So essentially what this model does is we have at the base plate a certain heat sink temperature, and then we apply in every step of the process a certain heat flux as it comes from the laser, all at once, the whole layer. And in that way, we generate the part. Now, if you do this, you get at each point in the part a peak in temperature where it was first deposited, and then several after peaks as the layers above it are also deposited. And what we are interested in is, particularly in order to prevent overheating, is this highest peak. And by taking this, post-processing all this data that we get from the simulation and taking these highest temperature values, we form this so-called hotspot map that indicates how hot a certain point has been in the fabrication history. Now that's what we want to obtain, but like I said, the computational cost is still too high. So there we observe that between depositing layers, actually usually there's some cooling time because a recoater comes by, there's new powder deposited and so on. And this cooling time, if that is sufficiently long to drop back to a kind of base temperature, you can decouple all the layer thermal simulations and do them also in parallel. Also, it allows us to drop the cooling simulation and only look at the heating phase. Then if you look at how heating works, is that the temperature only affects a local region. It takes some time in order to process through the part and progress through the part and heat up another region. So actually there's a limited length scale related to the thermal effect. And by taking that into account and only considering so-called slab, so a collection of layers that is relevant for the thermal response, we can also speed up the computation quite a lot by leaving out the rest of the part that is not relevant. And finally, and the biggest simplification we made is that we dropped the thermal simulation, the transient simulation, and replaced it by a steady state simulation. This is no longer accurate. This gives more like an indication rather than a true temperature value. You can also see that in these result plots. So these look still quite the same as before, but now by going from transient to steady state, quantitatively we get different values. But you can see that qualitatively the spots which are getting hot are still showing up in the same way. So quickly, because I think my time is running towards the end. This is the problem formulation that I'll show for the example problem. We still are minimizing the compliance, but we added this constraint on the maximum temperature that occurs. And for that, we do this slab-wise simulation of the temperatures, the steady state simulation, and identify the maximum temperature. And like this indicates this is our process simulation. And that ends up in this constraint. It's computationally still a bit expensive, but not clearly not as much as a real process model, because we have these smaller problems, and the sensitivity analysis, because we move to steady state, is also quite straightforward. To make this differentiable, to pick up this maximum, we again use a smooth maximum value. So here's an example of a topology optimization, standard topology optimization for, again, a beam without this hotspot constraint. And with hotspot constraint added, it seems at first sight nothing much has changed. But if we look at the hotspot maps, we see that this result actually avoided a hot region that you would get in a standard part. And similarly in 3D, the results are typically that what we see are subtle, but still important, because important hot regions are removed by this constraint. Now, final application example, that is where we applied this hotspot constraint to a real part. This is a mold for injection molding. And with standard topology optimization, we obtained this geometry. With the overhang constraint, so 45-degree constraint, we get this layout. And with the hotspot constraint, we get this one. So you can see they have a different effect because they also target different aspects of the fabrication process. And if we judge this by overheating, maybe not fair, maybe if you judge by overhang, you may get a different result. But if you judge this by overheating, you can see that in the two other cases, we get a clear hot regions while printing. So that could give problems. And in the one optimized for minimal hotspots, these regions are gone. So we're now in the process of also experimentally validating this result, and hope to report on that soon. Let me move then to the conclusions. One thing I can add is instead of optimizing the part, you can also use this for optimizing only additional supports for thermal reasons. But let me move to the final conclusion there. And I think the main conclusion is that with topology optimization, we have a very versatile method to optimize both the support, but also the supports for additive manufacturing. And for overhang control, yeah, I think it's a very nice topic, because there are so many ways to solve this problem and to approach it. I think the next talk will also show that. So I showed here 3 different methods, but I think this is definitely not the full story to it. And like I also have shown, build orientation, like was asked this morning, is a very important thing, and it is not trivial how to include that in these kinds of optimizations. So with that, thank you for your attention.
Thank you very much for a very interesting and broad-ranging talk. I think we have a little bit of time for maybe a couple of quick questions. There's nothing in the chat, so if anyone wants to, okay. Ferdinando has a couple of questions.
Hi, Matisse. How are you?
Hi, doing well.
Very nice presentation. Very, very nice. Many hints and ideas. So thank you very much. I have several questions, but I will focus on 2 specifically. Can you go back to slide 25? Maybe.
Yes.
With my computer, I miss. What is the reason for doing this front programmation based optimization?
Well, the reason is that we wanted to step away from the requirement of having a structured mesh, and then you can do a mesh mapping, like I said at the start. So basically, then you take this mesh, you map it to a regular domain, and then you could do everything as before. But in order to avoid that step, we thought it would be nice to create some way a field that indicates, just like in the other filter, which part of the domain you can actually print. And what we came up with is to use front propagation for that, because it's a fast algorithm known for also many other image processing tasks.
So, but why do you need a regular mesh?
Okay, then I should go back another slide, I think. I'm guessing here. Yes, this one. So imagine that this is an irregular mesh and that it's not aligned with the layers. Then I cannot use it to do this geometry-based simple way of indicating where the overhanging parts are. Or if it's a irregular triangular mesh, for example, then it also doesn't work. And also here, the overhang angle is tied to the mesh, because here I have a regular mesh with square elements, which means that I get nicely a 45-degree angle in the results, which happens to be the angle that technology can still print at this moment. But maybe in some years you want to have a different angle, and then you actually have to.
Okay, so the two things are related. Okay.
Yes.
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 Another question very quickly. Can you go to slide 33?
Yes.
Okay, great. Because when you show the temperature here, how did you get these temperatures? Because this seems to, I would say, less physical than the temperature that you show later on. So this pattern of temperature doesn't seem to be right, while the pattern that you get, for example, in slide 36 seems to be much more reasonable.
Yeah, that is very well spotted. So indeed, I should have maybe been more careful with experts.
No. But I'm just curious. So this was just rough.
Was more for illustration purposes. It is
okay.
It's already one of the simplified models.
Okay. I see. Okay. Thank you very much. I will send you an email and chat between the two of us because I have other questions. Thank you very much.
Great.
Okay. I think as we're into the next speaker's time slot, let's leave the questions there, and then we can continue them in the breakout rooms afterwards. Okay, so thank you to Matthias again. Could I invite the next speaker to start sharing?
Okay, you should see my presentation now.
Yeah, perfect.
Okay.
I can see it. So let me introduce our next speaker. So Francesco Mezzadri is based in the engineering department at the University of Modena and Reggio Emilia, and his talk is entitled Density Derivative-Based Approaches for Overhang Control in Topology Optimization for 3D Printing. Okay, go ahead.
Thank you very much for the introduction. And before starting, I just want to mention that this talk is based on joint research with Xiaoping Qian at the University of Wisconsin-Madison. So let us start with an outline of what we are going to discuss. And the context is the same of the speakers who preceded me. So for instance, this is a design which was obtained by a 3D printing process. Sorry, not by a topology optimization process. And so what you are seeing basically is the representation of a density function, which is 0, where the material is not present, so in the blue regions. And instead it is 1 in where the material is present, here represented with the color orange. These two regions are separated by a boundary, so when in the following we will talk about boundaries, we're referring to this solid void boundary, this boundary which separates the solid and the void regions of our design. If we want to 3D print this design, basically, we could encounter some difficulties. In particular, let us assume that we want to print this design along a vertical build direction. And we again find the unsupported parts which were discussed by the speakers before me. And so, for instance, in this top part, we would need to add support structures or to change the design. What we will do in this presentation is basically to try to solve this problem by an alternative approach with respect to what was analyzed in the previous talks. And in particular, we will analyze and focus on the role on the derivatives of the density function. So first, we will impose an overhang constraint. And this will require analyzing and imposing a constraint which is based on first-order derivatives of this density function. However, especially in the first talk of today, as we have already seen in the first talk of today, if we do so by a purely geometrical approach, then we may have oscillating boundaries, which of course are not acceptable. And therefore, we need to find a measure which identifies these oscillating boundaries and which can be used to suppress them. And we will see that this measure can be formulated by using second-order derivatives of the density function. Finally, we will see that by using these density derivative-based approaches, we can obtain designs which are free of non-self-supporting parts and also free of oscillating boundaries. Well, let us then briefly overview the framework of this talk. And again, we are interested in the possibility of 3D printing the result of a topology optimization process. And this is interesting because the optimized design can be very complex, can have very fine features, like in the example here reported. And therefore, the flexibility of 3D printing is very attractive in order to be actually able to manufacture these designs. However, we have the problem of overhangs, so we will not spend too much time on this, as it was thoroughly introduced by the previous speakers. But anyway, just to introduce some notation that we are going to use, we have a build direction, which we denote by the letter B. In general, for simplicity, we will assume this direction to be vertical and directed upwards, but it is very easy to formulate our approaches for any general build direction. So this is just a simplifying assumption to ease the presentation of the approaches, and we will also mention what happens for general build directions. And we will instead denote by the letter alpha the overhang angle. So if this angle alpha is sufficiently steep, well, we don't have any problem. The structure, the overhanging boundary, is self-supporting. However, if alpha is not steep enough, the structure may collapse during manufacturing. And so basically we have two paths we can follow. We either add sacrificial support structures, which of course, however, they will have to be removed after manufacturing. So we have a waste of material and also an increased cost for the processing. The alternative is to consider design that are self-supporting. We will focus on this second possibility, and in particular, if the design is the result of topology optimization, what we want to do is to basically introduce constraints or some filtering techniques, which basically forbids all the designs that present non-self-supporting boundaries from the possible solutions of our topology optimization problem. At the end of the talk, we will also, however, mention some implications also on the first possibility, which is on the computation of support structures. And we will briefly discuss how these density-based approaches can be useful also to compute optimized support structures. Let us then start with the approaches we are interested in, and in particular, let us introduce a density derivative-based approach to constrain the overhangs. In particular, we here summarize the projected undercut perimeter or PUP constraint, which is based on two very simple considerations. The first one is that the gradient of density, here denoted by the letter gamma, is different from zero only along the contour of the design. Indeed, if you take the part of the void region or any point of the region where we have full material, well, In both these cases, the density is constant. It will be 1 in the material and it will be 0 in the void region. And so, of course, if we compute the gradient of this density, we'll obtain a 0 value. At the boundaries, on the other hand, we have that density changes. It passes from 0 to 1, or also through a series of intermediate densities, if, as in this case, we are using material densities. But anyway, the gradient can be different from 0 only along the contour of the design. And this is what is also represented here on in this figure on the right. And the second thing that we notice is that the dot product between the gradient of density and our build direction will be larger than 0 in overhanging boundaries. And again, this is represented here on this figure on the right, where again, as always, we have assumed a vertical and direct build direction, which is also directed upwards. But at this point, it is also easy to relate the overhang angle alpha to the dot product gradient of gamma dot b. And this can be done directly from the definition of dot product. So we have this relation here, which basically, where basically alpha is the angle between the gradient of gamma and our build direction. However, by simple geometrical considerations, which are summarized in the figure, this alpha between the gradient of gamma and b is the same as the overhang angle. So we can exploit this relationship to formulate a self-support condition. So if we take exactly the same relationship and replace alpha by alpha bar, where this alpha bar denotes a given threshold, it could be, for instance, the specifics of a 3D printing process, then we can say that the boundary is self-supporting when the dot product between the gradient of gamma times b divided by the norm of the gradient of gamma is smaller than or equal to the cosine of this threshold in alpha. At this point, we have basically all that we need to formulate our constraint. In particular, by this relationship, we can well, in particular in the PUP, we use a shifted Heaviside projection to build a function, which is this capital H of alpha bar, a function which is non-zero only along boundaries which violate the self-support condition. Now, we don't have time to go into details for the mathematics, but basically, thanks to a shifted Heaviside projection, we obtain this function. But if this function is non-zero only along boundaries which violate the self-support condition, we can simply integrate over the entire domain and obtain some measure, some value which characterizes how many boundaries, how many non-self-supporting boundaries we have. In this case, in the integral, we have also this additional term, gradient of gamma dot b, which basically makes so that this p of alpha bar represents a projected overhang undercut perimeter, which is violating our self-support condition. At this point, if we require that this perimeter is smaller than a given threshold, this p bar here, then we are imposing a constraint which requires that non-self-supporting boundaries are sufficiently small, so to speak. And And in this way, we have imposed a gradient-based overhang constraint. This, however, as discussed also in the previous talk of today, although has some advantages, like it is simple, it has a direct geometrical meaning, and also we have a single integral constraint to be imposed to the topology optimization problem. So we have a good efficiency of the procedure. However, we also have the issue of the dripping effect. So a cheap way for the optimizer to satisfy our constraint is not to completely change the mechanics of our design, but simply to introduce boundary oscillations. And so the PUP constraint is not enough. Either we change the constraint, either we rely on the mechanics, or we change the basics idea of the overhang constraint, or we need to detect and suppress these oscillating boundaries. To do so, first, we need to analyze mathematically what these boundaries, these oscillations are, and to characterize them. Once we have characterized them, we can formulate a measure of boundary oscillations. And then, once we can measure boundary oscillations, we can formulate some approach, some technique to suppress them. Before doing so, let us just again introduce, make a few considerations and introduce some notation. In particular, we are going to call tip of a boundary oscillation these parts of the oscillation which are pointing outwards the design. Instead, we are going to call valleys the parts of the oscillation which points inward the design, as here. It is also interesting to notice that valleys of boundary oscillations and the top parts of holes are geometrically indistinguishable. So what we will do to suppress oscillations will not be to suppress valleys, because if we suppressed all valleys, we will end up suppressing all holes, and this is not what we want. So what we will do will be to suppress tips of oscillating boundaries. So distinguish tips from valleys and then suppress tips of oscillating boundaries. And how can we do this? Well, first, we simply analyze what is the difference between a tip and a valley. And in this regard, we consider the case where x is the horizontal axis and z is the vertical axis. And we analyze how our density gamma changes at a fixed height z hat. In this regard, for simplicity, we also define this capital gamma of x as the density at some height z hat. If z hat, this height, passes from the tip of an oscillating boundary, well, what happens is that, well, at the tip, the density is 1. We have material because the oscillation is present. However, we also have a neighborhood from this point, a neighborhood along the x-axis, where the density is 0. Is 0, or at any rate smaller than 1 if we are considering the material densities which change continuously, which continuity. And therefore, this point, the tip of the oscillation, can be seen as a maximum, a local maximum of the function capital gamma. In valleys and in top of holes, we have the opposite situation. Basically, at the very point where the valley occurs, we have 0 density. On the other hand, in a neighborhood at this height z equals z hat, the density will be 1. So in valleys, we are in a local minimum. This, well, it's not yet a characterization, but it already gives us a mean to distinguish between tips and valleys of oscillations. In particular, under some smoothness assumptions, we are going to have that the second order derivative of our density function with respect to x will be smaller than 0 at tips of oscillating boundaries, while it will be larger than 0 at valleys of oscillating boundaries or in the top parts of holes. And this is what we can indeed see here. In the top left, we have an oscillating design. On the top part of the figure, instead, we have a representation of the first order derivatives of the density function. And you can indeed see that the first order derivatives change sign at tips and valleys of oscillating boundaries. And in the bottom part of the figure, you can instead see a representation of the second order derivatives. So on the left here, we have a full plot of the second order derivatives, while on the right, down here, we have a representation of the negative values of the second order derivatives. And these figures, and maybe especially this bottom right figure, shows that while tips of oscillating boundaries are evidently characterized by negative second order derivatives, at values of oscillating boundaries, this is not true. We are going to have positive values, and when we plot only the negative values, these will just be 0. However, as I mentioned also in the previous slide, we still do not have, at this point, a full characterization of the oscillating boundary, because the second order derivative is smaller than 0 also along many other parts of the boundary, also in non-oscillating parts. So we need something more. We need an additional consideration and an additional derivative-based condition. The consideration is that if our oscillations arise to satisfy a geometrical overhang constraint, then we will all be facing downwards. And this means that the tip and also valley, and of course also valleys, will be characterized by horizontal overhangs. And in these regions, the gradient of density will be directed exactly upwards, exactly along the bill direction. And at this point, we can find the characterization which allows us to identify only the tips of oscillating boundaries. And this is done simply by considering both a condition on the gradient of density, which ensures that we are in a horizontal overhang, and also the negativity of the second order derivatives of the density function. In general, for a general bill direction, well, conceptually, it doesn't change much. We simply have to take into account the bill direction in our relations. So the first order relation is replaced by this relationship here, which involves the gradient, again, of gamma. The negativity of the second order derivative is instead replaced by the negativity of this quadratic form, which for compactness we name with the letter Q, where anyway we still have the second order derivatives of the density function. Indeed, this here denotes the Hessian matrix of gamma. And B orthogonal is simply the direction which is orthogonal to the given bill direction B. Therefore, by this characterization, we can finally write for any bill direction a derivative-based measure which detects tips of oscillating boundaries. And this measure in particular is made like this. Now we will analyze all the components of the measure itself. We have Q of gamma, which is simply the quadratic form we have seen in the previous slide. And it is negative at tips and positive at valleys and at top parts of holes. Its role then is to allow us to distinguish between these two situations, tips and valleys. H theta of gamma, well, this is a part, a term, which is used to basically detect the points that are in horizontal overhangs. So it is the same Heaviside projection which was used which is used in the PUP constraint. So it is the same function which we have already seen a few slides ago, with just a little difference, which is that theta, the angle theta, which denotes where, for which overhangs this Heaviside function is non-zero, is such that the cosine of theta is very close to 1. In fact, we do not want to, well, the threshold overhang angle basically is horizontal in this case. So we are just interested in something which is non-zero only in horizontal overhangs. So we just use the Heaviside function of the PUP paper with an overhang angle which is horizontal. Finally, this last term wouldn't actually be necessary. So Q of gamma times H theta would already be enough to fully implement the characterization that we have seen in the previous slides. The additional term of this dot product between the gradient of gamma and B is just used because it helps to detect boundaries more sharply. But we actually do not, it's not mandatory. We can actually not use it. But this measure then basically merges all the considerations we made above, and by how it is built, by how we have seen just now, M of gamma is negative on the tip of boundary oscillations, and it will be positive at valleys and in top parts of the holes, and it will be 0 everywhere else. And this is indeed what we can see here. So once we have that measure, we want to restrict our analysis to tip of oscillating boundaries. So we can project minus m minus our measure and consider only the negative regions of m and project everything else to 0. And so we define this m hat, which of course will be 0 everywhere except at tips of oscillating boundaries. In practice, if we need sensitivities, we will equivalently use a differentiable approximation like this one here, which we call m tilde. And it is now easy to verify that this measure basically works as we want, as we hope. So in the figure, we again have our usual oscillating design. On the top right, we have a representation of minus m of gamma. And you can indeed see that this function is larger than 0 only at tips of boundary oscillations, while it is negative at valleys of boundary oscillations and also in top parts of holes. If then we apply either the projection of m hat or the differentiable approximation, we obtain the results in the bottom here of the figure, respectively on the left for m hat and on the right for the differentiable approximation. And we see that these two functions are 0 everywhere, except where tips of boundary oscillations occur in our oscillating design. At this point, we can exploit our measures to develop various strategies to control boundary oscillations. For instance, we can use an adaptive PD filter. This idea follows what was done in the original PUP paper, where a smoothing and elliptic regularization was used to basically suppress oscillating boundaries. However, this had also various counterindications, because if we use a PD filter with large filter radius everywhere, then we are also closing holes, we are losing features, we are increasing grayness. And therefore, what we can do with the boundary, with our measure of boundary oscillation is to conceptually proceed in the same way, but use our measure in order to use a large filter radius only where and when is needed, thus limiting the disadvantages of a large filter radius. In alternative, we can also formulate explicit constraint or cost penalization, which directly impose in the topology optimization problem that oscillations are not present, basically. Now, we are not going into details, of course, just to give you the general idea of our implementations. Well, regarding the adaptive filter, integrating m hat in this case, so the exact projection of the measure m in the entire domain, we can obtain a value here denoted by this capital M hat. And based on the values of this capital M, we can decide whether to increase or to reduce the PD filter radius. In this case, we can use a non-differentiable projection because actually we do not need density, we do not need sensitivities. So this is just a measure which guides us. But yes, basically, it is not involved directly in the topology optimization problem, and so we don't need it in the sensitivities. Regarding the cost penalization, well, regarding the constraint in our case is we formulated it as a cost penalization. So we have computed the P norm of our differentiable approximation of M hat. And then we have added this P norm with P quite large, so to have an approximation of the uniform norm of M tilde. We have added this capital M tilde to the cost, applying also a weight W, which basically is just used so that the penalization and the original cost function have a comparable weight. Just a couple of words of what happens in 3D, while conceptually it doesn't change much. Indeed, this figure here represents a 3D representation of an oscillation in a plane x, y, z, in a space x, y, z. And if we take the plane at a given height z hat, the tip again is a local maximum. We have one density here at the very tip of the oscillation, and then we have a neighborhood where the density is 0. So we can proceed exactly in the same way. Instead of having directly the sign of the second order derivative, however, we will have the sign of the 2x2 Hessian matrix. But again, this can be studied considering the sign of the minors, which involved, in turn, the sign of the second order derivatives of our density function with respect to x and y. Let us then pass to a few numerical experiments, and we will consider a 2D problem and a 3D problem. And these, for instance, are the results we obtain for when we use the adaptive filtering technique, our implementation of the adaptive filter, for different thresholds to the overhang angle. We here have 30 degrees, 45 degrees, and 60 degrees. In all cases, we can already see that we do not have boundaries which violate the self-support condition with the prescribed angle, and we also do not have oscillating boundaries. At this point, however, we also wonder if we have some advantage with respect to using also the PUP constraint with large filter radius everywhere. And basically this question is replied to in the table. Here, C denotes the final value of the cost for the three represented designs. The cost here, of course, is the compliance. Delta C instead represents the reduction of this final cost, so how much our cost is better, so to speak, with respect to the best non-oscillating designs which were obtained with the PUP constraint alone. So basically for not critical, so to speak, thresholds to the overhang angle, we have an improvement around 10%, and this improvement becomes more and more significant with stricter thresholds to the overhang angle. MND finally is a measure of non-discreteness which just ensures that our designs are sufficiently sharp and we do not have too many intermediate densities. With the cost penalization, well, we can repeat the same considerations. The saving in terms of the cost function is even more remarkable for 45 and 60 degree cases. And instead, we do not have a particular advantage when the threshold to the overhang angle is just 30 degrees. The cost in this case is almost equal. It is also just a little worse. But anyway, for the other overhang angle, the saving is very significant, and it is almost half, especially in the 60 degree case, with respect to the PUP constraint alone. Regarding the 3D problem, well, this slide only shows that also in 3D, we are indeed able to detect oscillating boundaries by the measure of oscillations. And in particular, the yellow region represents the zones where the 3D version of our second order measure of oscillations is different from zero. And here on the right, in this zoom in, you can see that these yellow regions correspond exactly to where tips of oscillating boundaries are present. Therefore, we can, again, apply the adaptive filter. And so here in top left, you have the design without adaptive filter, which has a given cost. And when we use the adaptive filter based on our second order measure of oscillation, of course, together with the PUP constraint, which is present also here on top left, then all these oscillating boundaries are suppressed with just a mild increase of the cost function. If, on the other hand, we used everywhere, at every iteration, and without any adaptiveness, a large filter radius in the entire design, we would obtain this design in the bottom right part of the figure, which has a much higher cost. In particular, when I'm saying large filter radius, I mean that the filter radius, which is here used everywhere, is used in the adaptive filter only where and when is needed. So these are basically linked by the maximum filter radius which is used, but with very different results. The same applies with the cost penalization, and also in this case, we have an unconstrained design. Unconstrained meaning regarding oscillations, we still have the PUP constraint. When we apply the oscillation penalty, all this oscillating part is replaced by a pillar, and a similar situation happens also on the left part of the design. So let us just briefly discuss an application in support structure. This is what I mentioned towards the beginning of the talk, which is, in some cases, we need to manufacture a specific design, and we cannot change it. So in this case, we need to use support structures. We can nonetheless try to use topology optimization to, well, make this, save some material, and so save the overall process. And in particular, we could try to compute some optimized support structures by solving a topology optimization problem, which is the one here summarized by the figure. And we actually did this, so we also 3D printed the optimized the support structures that we computed, for instance, to support the horizontal overhang of an MBB beam, or to support the dome, or this bottom right case here is it's the mascot of the University of Wisconsin-Madison. And these optimized support structures are generally self-supporting, but this is not always true. We can have overhangs also in optimized support structures. Not often, actually, but it may happen. And so, in these cases, as in the case represented here in the figure, it may be it is necessary to impose some overhang constraint, like the density derivative-based approaches, which we have seen now, to ensure that the support structure is indeed self-supporting. And this is exactly what we did here on the right, where the support has been computed with also the addition of a overhang constraint. So, concluding, we have seen approaches that are based on the analysis of derivatives of the density function, and we have seen that we can actually use them to detect overhangs and boundary oscillations. By the measures that we have introduced, we can then implement some overhang control strategies, and we can do this by a variety of filters, constraints, or penalizations. And also what we have seen now are just some examples. We could exploit the generality of the introduced measures to formulate many other filters, constraints, and so on. And we have also shown numerically that we can actually apply these techniques also in 3D problems to obtain self-supporting and oscillating free designs. Thank you.
Thank you very much for a very interesting talk. I don't see any questions in the chat, so if people want to just directly unmute to ask a question, please go ahead. Just give people a minute. Okay, I think
I have a question.
Yeah, go ahead, Nicola.
Thank you for your talk, which is the inspiration to the last part of my talk, because basically the master student who worked on this had some hints on the first work without any filtering and stuff, but the basic one. I was wondering, which function space do you choose for your density, since you want to compute high order derivatives, at least
Yes.
second order derivatives? Do you have any strategies to suggest?
Yes, as a matter of fact, yes. Well, in the discussion, in the analysis of the measure of boundary oscillations, and also into the experiments, well, we used basically CG2 elements, so elements of order 2. However, in 3D, and we have basically expressed the second order derivatives by a weak formulation, which allowed us to use first order elements. Of course, these, on a strictly mathematical point of view, would not satisfy the smoothness assumptions of our characterizations. However, in practice, we noticed that also using this weak formulation, so to speak, we can detect tips and, of course, also valleys of oscillations, of oscillating boundaries. In this regard, I take advantage of this question to point out that the adaptive filtering technique is particularly efficient in this regard, because you don't have to compute the measure at every iteration. We did it, for instance, every 25 iterations. If you add to this fact the use of order 1 elements, which you would need for the PUP constraint, then the overall overhang control by adaptive filtering is expensive. Like the PUP constraint, you cannot really see a difference. With the penalization, you have a more rigorous formulation, and also there the cost is not, well, if you use a CG2 element, of course, the cost is, of the computational cost is much more, is more significant. But again, with instead using CG1 elements, as I mentioned earlier, you can really limit the computational cost also when you use the penalization.
Thank you for your answer and your insight.
Thank you for the
topic.
Will, I have a question for the first speaker.
Should we maybe move into the breakout rooms, or is that, would it be a good question to add?
No, I think that we are all in the same room, in the first room. Usually,
right, okay. In that case, let's throw it open then.
Should I remove the share? Okay.
Yes, please.
I'll do it immediately. Okay. Here, done.
Okay, so I have a question for the first speaker. I think he's still in, right? Matthias Langelaar.
Yeah.
Okay. So you mentioned you mentioned one of the difficulties you have for the solution of the Conal equation.